Curves in industrial design, from Bezier curves to B-spline curves. Although Bezier curves are good for design, they present some issues. For example, they are non-local, which means that when we move a single control point, this movement affects the position of every point on the curve. From the design point of view, editing a curve near a point alters the whole curve, which is not desirable. We also need high degree when we want to model a complicated shape with just one Bezier curve. For curves with high degree, the control polygon can be far from the curve. Also, if we want to add details on the curve, we need to add control vertices, which means we need to increase the degree of the curve, and hence we need to change the whole curve. All these problems are easily solved by joining several Bezier curves together. On the screen we can see an example of a single Bezier curve of degree 6, 3 Bezier curves of degree 3, each of them in a different color, and 5 Bezier curves of degree 2, also in different colors. These are the respective control polygons. This is the control polygon of the single Bezier curve of degree 6. These are the 3 control polygons of the 3 Bezier curves of degree 3, and these are the 5 control polygons of the 5 Bezier curves of degree 2. From the previous examples, we can observe that the union of quadratic Bezier curves is a smooth curve because it has no corners, but it's not very round. This is because its curvature is not continuous. This is what we call a C1 curve. Also, from the previous examples, we can see that the union of cubic Bezier curves is a smooth curve, it has no corners, it is very round, that means its curvature is continuous, but in this case, the derivative of its curvature is not continuous. This is what we call a C2 curve. In general, a curve is said to be CK if the curve has k continuous derivatives. On the screen, we can see 3 quadratic Bezier curves, and from them we want to construct a single smooth curve, that means a quadratic B-spline. To get a continuous curve, a single curve, we need to move the vertex C3 to the position of the vertex C2, and the vertex C6 to the position of the vertex C5. We do so by moving the slider. If we want to move the control vertices and keep a continuous curve, the vertex C3 is always first in the same position of the vertex C2. So now the vertex C3 is not free to be moved, and therefore is not part of the control polygon of this curve. The same happens with the vertex C6. If we want this curve to keep being continuous, it has to be moved, always be in the same position as C5. So it's not free to move, and it's not part of the control polygon of this curve. This is a continuous curve, but it's not a smooth curve because it has a corner at C2 and at C5. So we smooth it out by moving the slider B. The resulting curve is a continuous smooth curve. But now the vertex C2 is not free to be moved. Its position is forced by the position of C1 and C4. We can see that C2 moves when we move C1. And the same happens with C5. Its position is forced by the position of C4 and C7 and is moved when we move these vertices. So now only the vertices in blue are free to be moved, and they constitute the control polygon of this curve. This is the control polygon of the B-spline curve. And the union of the Bezier curves forms the quadratic B-spline curve. So in general, to join S quadratic Bezier curves, each Bezier piece is defined by 3 control vertices. So at the beginning we have a total of 3 S vertices. To make the union a continuous curve, at the joins we are forced to move one of the vertices to be in the same position as other vertices. So this reduces the number of vertices by the number of joins, which is S minus 1. So from 3S we need to subtract S minus 1 and we get 2S plus 1. Also, if we want to make the union a smooth curve, again another control vertex is not free to be moved in the join. Its position is forced for other control vertices, and this reduces the number of vertices in the control polygon by S minus 1. So now we have to subtract this number to 2S plus 1 and we get S plus 2. The smooth union of S-quadratic Bezier curves has S plus 2 vertices in its control polygon. We call a uniform quadratic B-spline curve continuous union of S Bezier quadratic curves. The union is defined in such a way that the resulting curve is C1. The B-spline control polygon has S plus 2 vertices, D0, D1, ds plus 1. The B-spline is called uniform because each Bezier piece is traversed in the same amount of time h. So the first Bezier piece is parameterized by t between u0 and u0 plus h. The second Bezier piece is parameterized by t between u0 plus h and u0 plus 2h, and so on. So the full B-spline curve is parameterized by t between u0 and u0 plus s times h. Now on the screen we can see 3 cubic Bezier curves. And as we did before, we want to join them to construct a single B-spline curve that is C2 curve. To get a continuous curve, the first vertex of the control polygon of the curve has to be in the same position as the last vertex of the control polygon of the previous curve. We do so by moving the slider A, and now we get a continuous curve, and the vertices in black are no longer free to be moved. So we lost one vertex at every joint. This curve is continuous, but it's not smooth. We smooth it out by moving the slider B. And again, at every joint, the vertex C3 in this case and the vertex C7 are not free to be moved. Their position depends on the first case on the vertex C5 and C2 for C3, and for C8 on C6 and C9. So the position depends on these vertices. So again, only the vertices in blue are free to be moved. Finally, we get the smooth curve that is continuous, but its curvature is not continuous. So we get a continuous curvature by moving the slider. When we get a continuous curvature, this condition forces the position of the vertex C5 in terms of the vertices C2 and C6, and the same with the vertex C9. Its position is forced by C10 and C6. Only the vertices in blue are free to be moved, and that next to every joint we lost another vertex to the freedom to move these vertices. These vertices in blue don't constitute the control polygon of the B-spline curve, although they are the same in number as the B-spline control polygon. The B-spline control polygon is this set of vertices, and even if we move them, the resulting curve is going to be always a C2 curve. This curve is going to be the B-spline cubic curve. So in general, to join S-cubic Bezier curves, each Bezier piece has 4 control vertices at the beginning. We start with 4 S vertices. To make the union continuous, a control vertex is absent at every joint because it cannot be freely moved. So now we have to subtract the number of joints, S minus 1, to the number of vertices for S, and we get 3S plus 1. To make the union a smooth curve, again, we have to subtract the number of as many vertices at joint. So we have 3S plus 1 minus S minus 1, which is 2S plus 2. And finally, to make the curvature of the union continuous, again, we lose a vertex at every, that is next to every joint, so 1 per joint. We have S minus 1 joints, so we have a total of 2S plus 2 minus S minus 1, which is S plus 3 vertices, free to be moved. The smooth union with continuous curvature of S-cubic Bezier curves has S plus 3 vertices in its control polygon. A uniform cubic B-spline curve is a continuous union of S Bezier cubic curves. The union is defined in such a way that the resulting curve is C2. The B-spline control polygon has S plus 3 vertices, D0, D1, ds plus 2. We call the B-spline uniform because each Bezier piece is traversed in the same amount of time h. That means that the first Bezier piece is parameterized by t between u0 and u0 plus h, the second Bezier piece by t between u0 plus h and u0 plus 2h, and so on. The full B-spline curve is parameterized by t between u0 and u0 plus s times h.